Okay, continuing on with the METOS series of videos, we'll talk about disease models for pulses. So just like every other crop, there's biological factors for that disease. In this case, it's the same. The environmental conditions need to be conducive for the development of that fungus within that particular crop of pulses. So it's assumed that the crop, the host, and the pathogen are present at the same time in the region. The plant disease results only if all the other factors occur at the same time. So if it's a new disease in a region and the inoculum levels for the pathogen may be too low, and that does not cause a disease outbreak. So the disease triangle really explains this. You have the environment, the pathogen, and the host. The environment tips the scale, so to speak, in favor of the pathogen to overwhelm the natural defenses of the host. So you need to know the local conditions at that particular field. So things like the temperature, the humidity, leaf wetness, precipitation, sometimes soil temperature are critical to understand the disease cycle going on for the particular crop. In this case, you're looking at initial infections from the pycnidia to secondary infections throughout the year from the conidea as well. So it's very important to have localized weather data. It's very clear here when you look at something like this scenario where we have a station at the main office and one at a field only 1.5 kilometers away. The differences in humidity and temperature and precip drive a completely different scenario, and as well the crop canopy. So in this case, we can see the field excellent site has a much longer period for disease development and infection because of high humidity and longer leaf wetness periods than the one that's at the main office under grass that has localized conditions that are shorter for disease development, lower humidity, and periods without leaf wetness as well. So you can't design a network of field models based off of data that is 10 kilometers away. It just won't work. You've got to have a device that's in or near that field to provide proper data to drive the model process. So you have to design this whole network based on the customer distribution, field locations, and the geography of the area. So for the pulse production in FieldClimate, we have a series of models: Botrytis, Sclerotinia, Alternaria, and Ascochyta. Today we focus on Ascochyta. It's really, as we know, the yield potential is set by the genetic traits of the crop, but that's mitigated, of course, based on factors throughout the year, such as pests, diseases, and field management practices. So the value proposition for pulse diseases models in FieldClimate is a strong one. With site-specific weather station data, we can really know the modeled conditions for disease risk, time our fungicide applications based on the actual conditions and disease risk pressure, which allows us to either stretch or shorten that spray window. We can preserve the yield and quality of the crop based on the well-timed fungicides as well. So we become very efficient in our management. We preserve yields is our value proposition. In particular, the pulse disease model for Ascochyta works in this way. It predicts the development of pycnidia and conidea during the growth season, so the initial infection and then the secondary infections that occur throughout the year. So the Ascochyta blight model looks at optimal temperatures for the development of the disease between 20 and 21, but there is a range between 4 and 34 degrees Celsius. But the key is the moist conditions, and that's driven off of things like high humidity and leaf wetness periods. So we implement this model in a two-step process for this disease cycle. We have the sporulation event, which we'll see, which is the development of the pycnidia that releases the conidea, so producing the new infection units that can affect new leaves and material, and then the optimal conditions for further infections of those conidea as well. So the sporulation takes place if it reaches 100%, and afterwards the infection curve reaches 100%. You then have very optimal conditions for the infection of the plant tissue at the field level. So looking at it in software, we have our Ascochyta blight model under pulses. We can see a period of time here stretching from June to late August, and we can see events where sporulation took place, and then the infection conditions occurred, sometimes very low, sometimes reaching 100%. We can see the same for sporulation. We can see sometimes 100% sporulation and sometimes very low. And we can see here we have a sporulation event, 100% infection, and we can see high periods of humidity, leaf wetness, and optimal temperatures. And then a period over time where we had less because things dried out, less in terms of the overall sporulations, and the infection rates were lower than 100%. And then again in August, another period of fairly significant infection based on a high sporulation period, long sporulation period. So if we look at that in detail, we can see an event here on May 13th where we reached at 7 p.m. 100% sporulation, and then the infection period took place, and that reached on May 14th at 1:30 p.m. 100%. And that's driven off of, as you can see, high humidity and long leaf wetness periods. So because of optimal conditions, the sporulation of pycnidia was determined here on May 13th at around 7 p.m. And then the conditions were still optimal for the start of the infection period because of this continuing high humidity, and it reached 100% again on the 14th at 1:30 p.m. So dependent upon the plant strategy for protective measures, they should be taken into account before the infection took place or using curatives slightly after the infection. So somewhere in here when the infection is taking place is your comfort level. Is it 40, 50, 60, 70% where you want to apply your fungicide? And that's what this tries to show us here, is that we do have a recommended window of where we can apply, and then the actual symptoms may not show up for 2 to 4 days depending upon the conditions that one has at a particular location. But it's all driven off of the ideal temperatures, leaf wetness, and humidity periods. So for Ascochyta blight, there is a cost benefit. You want to make a calculation on the economic threshold or the break-even point of when you should spray for it. So the potential yield loss is times by the estimated yields pound per acre times the price will give you the yield loss per acre. So if the value is the cost of the fungicide application is lower than the cost of the fungicide, then do not apply. If the value of this is higher than the cost of the fungicide, fungicide is warranted. So a couple examples on two different crops. So if we look at a 2,400 pound at 24 cents per pound and an application cost of $22 and a yield loss of 15%, the variety rating is poor of this particular one, then our formula would be yield loss times 2,400 times 24 cents, or $86 per acre. So at $22 an acre, it's very economical to apply the fungicide on an $86 per acre loss. On another crop, if we had a yield of 1,800, 16 cents per pound, and a 7%, a low disease risk, we'd come out to $20 per acre, which is less than the $22 an acre. So it's not economical. However, looking at it on a 1,000-acre crop, we're losing between $20,000 to $86,000 based on that yield loss. At a cost of $3,000 per year, your IoT system is going to let you know your conditions in your field and could potentially return up to 8 to 1 on your investment. So there is a good benefit here. You know before you go. You save time and money knowing your fields with your data. You have verified weather conditions in that field from your devices. You have verified model infection conditions in the field. You can look at verified severity levels and sporulation events in the field. You can determine your spray timing based off of the model, the date and hour, as well use the system for looking at optimal conditions for spraying. Is it a good time to spray based on the environmental conditions? And it gives you a past record of what went on in your field in terms of the infection levels and weather conditions. Thank you for your time.